Section 4.1 we talked about maximums and minimums and how that relates to a derivative. Now we're going to look at how a function increases and decreases in relationship to a derivative. So when I look at a function, I'm looking at a function, I'm reading it from left to right. And the slope of the tangent line as I'm looking at this function from left to right, the slope is positive. And the y values are all increasing. So we say that this function is increasing. And conversely, we look at this one and the slope as I read this function from left to right. The slope is negative, and therefore we say that this function is decreasing. Now, sometimes you can kind of get mixed up in this because you'll be looking at a function, say let's look at this function here, and it kind of looks like it's always going down. But I want you to look at this function as you read it from left to right. And as I walk along this line from left to right, this function is increasing and then it is decreasing. So if I were asked for the intervals of increasing and decreasing, I would say it was increasing from negative infinity all the way up to 0, and then it is decreasing from 0 to negative infinity. And I don't use the square guy brackets on this because I don't say that it increases or decreases at a point. Alright, this is a theorem that allows me to test for an interval of increasing or decreasing. So if f is continuous on our interval and differentiable at every point in the interior, we know that if the derivative is greater than 0, otherwise known as the slope is greater than 0, then f is increasing on that interval. If the slope is less than 0, or if the slope is negative, that means that it is decreasing. Well, that was what we basically just talked about in the last one. So we're supposed to sketch a function, and everyone's function in this can be different. It's going to revolve around this point 0, a 4, and a 6. I'm just going to kind of draw a rough sketch, and then I'll draw something that looks a little better, because I might not draw it exactly right the first time. Let's see. From negative infinity to 0, it's got to be increasing, so it's got to be doing some sort of going up. Then from 4 to 6, it's also going to be going up. So see, it looks like it goes down here, so I'm just going to go down here, and then here it goes up, and from 4 to 6 it's still going up. Okay, and I drew the down one. F, the derivative at 0 is undefined. It's probably, since it's continuous, it's probably some sort of corner, so we'll just do this. At 4 and 6, the derivative is 0, so means it kind of does this right here, changes direction there. Oh, and it's got to, okay, so that's just going to kind of do like this, where it levels out and then still goes back up. Alright, so let me put it down here. Actually, it's not too bad. 4, 6, so I want it to, and then I want a corner, and it's got to go down. At 4, it's going to turn, and then at 6 it's going to level off and then go back up because it's still increasing. There's my function. I need to find the intervals in which the function is increasing and decreasing. I'll need to find f prime. I'm going to use the product rule, take the derivative of the first, that's 1 e to the minus x plus x, take the derivative of e to the minus x, that'd be negative e to the minus x. This is going to be, I need to combine this into one big chunk because I need to figure out if it is where it's 0 or undefined. I just should have put that as a minus. Oh well. Okay, so this is going to be 1 minus x over e to the x. E to the x is never 0, so it's not going to be undefined. So I have one critical point. That critical point is at x equal 1. So I know that at 1, the derivative is 0. So what I need to do is see what is the derivative on the right side of 1. Say I could make 1/2, but I don't like to make it easy on myself, and I'm going to see what it is at 2. And then I'm going to do it over here on the left side. I'll do it and make it easy on myself. I'll do it at 0. So what is the derivative? And I don't really care what the number is, I just care what the sign is, because if it is positive, it's increasing. So at 0, that would be a 1, that's positive, so this is positive. So it's increasing on the left side of 1. On the right side of 1, I put in a 2, that's a minus 1, and that's always positive, so this would be a negative. That means that this thing is decreasing on this side of 1. If I look at the actual function, I can see that the slope is increasing. At 1 it becomes 0, and then from 1 on it is decreasing. Now, that's an observation made from a graph. I don't know if this function's going to do some little whirly-gigs out in here, because when you just graph it with your calculator, you're only looking at a certain window, and you don't really know what it does out in this other realm that might not be in your window. But when you take the derivative and you find the critical points, so x equal 1 is a critical point, you know that that's the only place that you could possibly have a maximum or a minimum. Therefore, I know that this function is always increasing from negative infinity up to 1, and it is always decreasing from 1 to positive infinity. And I know that this doesn't happen out there, but I wouldn't know that by just looking at a graph on my calculator. So I'm going to play this game. F prime of x equals 6x squared plus 6x. Need to find the place where it's 0 or undefined. I'm going to pull out a 6x here, and that's going to be x plus 1. X equals 0 and negative 1 are critical points. I need to check to see if it changes directions. So 0, whoops, shouldn't have put that at 0. Alright, fixed it. I know that the derivative is 0 here, which means that at negative 1 I have a horizontal tangent line. I need to know what it's doing here on the left side of 1. How I prove that is I pick some number on the left side of 1, because these are the only places where you could have these turning points or these maximums or minimums. So I'll choose negative 2. I'll plug that into the derivative and see if it's going to be positive or negative. So I would have negative 12 here and negative 1 here, so it would end up being a positive. Therefore it's increasing from negative infinity all the way up to 1. Let me choose something in between negative 1 and 0. Nothing really strikes my fancy. I'll choose a half, but I don't really care what the number is, I just care what the sign is. So I'm choosing negative a half, excuse me. That's negative, that's a positive, so this would be a negative answer. That means it would be decreasing from negative 1 to 0. Plug in something here on the other side of 0. Can be anything you want. Can be a 2, a 4, it can be a million if you want, but it's going to be positive. That means it's going to be increasing. I would write this as increasing from negative infinity up to negative 1, and from 0 up to infinity. And it is decreasing, negative 1 to 0. This theorem is formally stating what we can see if we have some critical point C and the slope goes from positive to negative. C must be a maximum. That's for this first one. 2. if we have a critical point and it goes from negative to positive, we must have a minimum. If it doesn't change sign at all, then there's no local extrema and we don't really know what it does. And this is just a summation of that. We can go through here. We see that the derivative is 0 here, but there's no extreme. We had one like that in that graph that we drew. It goes from positive to negative, therefore it must be a max. Negative to positive must be a min. The derivative is undefined here, so and it is a critical point, and it goes from positive to negative, therefore it's a max. No extremum, it's just going from negative to negative, so we just have some sort of horizontal tangent line there. Working really the same problem that we did just a minute ago. We're going to find where it's increasing and decreasing, and then we're going to use our theorem 4 to state whether it is a maximum or a minimum. So f prime of x equals 12x cubed minus 12x squared minus 12x plus 12. Okay? Need to find the place where the derivative is 0 or undefined. I'm going to pull out that 12x cubed minus x squared minus x plus 1. And I am going to do something called factor by grouping here, because I need to know where this thing might be 0. So I'm going to look at these two factors, and I'm going to look at these two factors. And these two, I'm going to pull out an x. I'm going to do this here. X squared. And I have left an x minus 1. These two, because I want it to kind of look like this, I'm going to say that I'm going to pull out a minus. And if I pull out a minus, then you'd be an x and you'd be a 1. I contrived that on purpose. 12. I'm going to pull out this x minus 1 factor. And what I'll have left is x squared minus 1. This thing factors into x minus 1, x plus 1, x minus 1. My possible critical points are x equal 1 and negative 1. Alright, I draw my number line here. Negative 1 and 1. I'm going to choose some point to the left of negative 1, say f prime of negative 2. And here, and then what I'm going to do is I'm going to see if this has got a positive or negative slope. When I plug it in, I don't really care about the value, I just care about the sign. So plugging in a negative 2, that would be a negative, that would be a negative, that would be a negative, so my answer would be a negative. So this thing is going down. F prime at 0, oops, 0, that's going to be a negative, positive, negative, so this is going to be a positive, which means it's going up from negative 1 to 1. Choose something to the right of 1. I'll choose a 2, and that would be a positive, positive, positive. This would be increasing. This tells me that x equal minus 1 is a local minimum. And I will write the intervals of increasing and decreasing. And the interval of increasing would be from negative 1 to 1, and from 1 to infinity. Decreasing, negative infinity to negative 1. Now I need to see if this is an absolute minimum. No, they just wanted local extrema. I still could tell you, because since these points are all above and this one doesn't go back down, I can tell that it's an absolute, but they didn't ask for that, so I'm not going to state there. Next we get to play with this one again. F prime of x using the product rule. 2/3 x to the minus 1/3. Leave the second one alone. 2 minus x plus first one. Take the derivative of the second. That's a minus 1. This ends up being 2 times 2 minus x over 3 cubed root x plus negative cube root x squared, getting a common denominator. I'm going to multiply this guy top and bottom by 3 cube root x I will end up with 4 minus 2x. This will end up being a minus x all over, oh yeah, there's a 3 in front of there. There we go. And on this denominator here, I'm going to have 3 cube root x. Good. So I have 4 minus 5x all over 3 cube root x. I need the places where f prime is undefined. X equals 0 and x equal, move the 4 over, that would be 4/5 are critical points. Now I need to figure out where it's increasing and decreasing, so I draw my number line. 0, 4/5. Choose something to the left of 0, f prime of -1, let's say. I don't really care about the value, just the sign. This will be a negative, making that positive. This will be a negative. That means this thing is a negative and it is going down. Oh, let's say a half. I hate it when it's a fraction in the middle there. So at a half, this 5/2 would be less than that 4. So that's going to end up being a positive. So I'll be increasing there. F prime at, I'll choose a 1. That's a negative, that's a positive. This will be a negative. It will be decreasing. Looks like I have a local min at x equal 0, and I have a local max at x equal 4/5. It goes down then up. 0 has to be a minimum. It goes up then down. 4/5 has to be a maximum. I can look at the graph, of course, and see that I have a local minimum here and a local maximum here. I'll break this video into 2 parts, so this will be part A, and I will complete section 4.2 in the next video. Hope to see you there. Bye.